Okay, in the last video we discussed the rules for determining whether different algebraic objects were infinitesimal, finite but not infinitesimal, or infinite. However, there were four algebraic expressions that are not categorized. So the first, we have what happens if I take the ratio or the fraction of two infinitesimals. Is that going to be finite? Is it going to be infinite? Or is it going to be an infinitesimal itself? And it really depends on the nature of those two infinitesimals. If we don't know anything about them, then they can't be categorized. And we'll look at three examples here. Sorry, my pen is acting up. There, so if I take the ratio of two infinite numbers, I also don't know. And then if I take the product of an infinite number and an infinitesimal, I don't know. And then if I take the sum of two infinite numbers, I don't know. And let's kind of see why these are issues. So in the tables right out of the book, here's why these are indeterminate. Because, for example, if I took epsilon squared divided by epsilon, both of those are infinitesimal numbers. However, and their ratio, epsilon squared over epsilon is simply epsilon, so clearly that's an infinitesimal. However, if delta and epsilon are equal, I could take their ratio, like this example, and this is equal to 1. Clearly a finite number, but not infinitesimal. And then this, again, if I do the algebra, is 1 over epsilon, which is an infinite number. So that's why the ratio of two infinitesimals is indeterminate. It depends on the form of epsilon and delta. Similarly, with the ratio of two infinite numbers. Right? This example, h over h squared, simplifies to 1 over h, which is an infinitesimal, whereas h over h is 1, and h squared divided by h is simply an infinite number. What if I multiply two infinite number and infinitesimal? Well, again, here's an example. This is also 1 over h. It is actually exactly identical to the above expression, but 1 over h squared is infinitesimal, whereas h is infinite. If I multiply them together, I get an infinitesimal. This is equal to 1. This is equal to h again. So we can see that I can have all three cases depending on the structure of epsilon. So in this case, our epsilon, our infinitesimal, was related to the infinite number in all three cases. And finally, what happens when I add two infinite numbers? Well, the problem here is we don't know if this is a positive infinite number or a negative infinite number. If they're both positive infinite, then it's going to be positive infinite. If they're both negative infinite, then this will be negative infinite. The problem happens when they are different signs. So the first example here, I have h plus negative h, which is equal to 0, and that is clearly an infinitesimal. Whereas h plus 1, infinite number, plus minus h, negative infinite number, is equal to 1, and then h plus h is equal to 2h. Again, since they're both positive infinite, it stays positive infinite. So that's why these four scenarios are somewhat tricky to work with. And what you end up having to do is work out the algebra to determine, to get it into some form that you can recognize. So be on the lookout when you're working these categorization problems for indeterminate forms. That's the ratio of two infinitesimals, ratio of two infinite numbers, the product of an infinite and an infinitesimal, or the sum of two infinite numbers. So let's jump right in and do some examples. So let's assume that epsilon and delta are both positive infinitesimals. Remember this symbol here, the double script E, is for the set of infinitesimals. And we'll say that h and k are positive infinite numbers. So again, this double script M is our denotion or denotes the set of all infinite numbers. I put a positive on it to say we only want the positive ones. So now we'll be okay. If we need to add two infinite numbers, we'll be good. So let's determine whether the given expression is infinitesimal, finite but not infinitesimal, or infinite. So first example, let's get back to yellow. First example, say, let's look at epsilon divided by h. So this is one where we could go right to our rules. This is not an indeterminate form. We can go right to our rules, and if we go up here in the ratios, if I take a infinitesimal and divide by an infinite number, that is itself an infinitesimal. Again, I'll walk through how I suggest that you work this out, and seeing that this actually as a product, this is epsilon times 1 over h, which since this is an infinitesimal, right? It's an infinitesimal. Then, and so is this, and the product of two infinitesimals is an infinitesimal. So this whole thing stays an infinitesimal. All right, how about, let's look at, say, the ratio of the square root of epsilon plus epsilon, all divided by root epsilon over 1. Now, first question you should ask, is this an indeterminate form? Well, indeterminate forms are infinitesimal divided by infinitesimal, infinite divided by infinite, products of an infinite and infinitesimal, or sums of infinite numbers. And at first blush, this may look like it's a ratio of two infinitesimals, but actually the bottom, yes, that's an infinitesimal, but when I add it to 1, this bottom part is finite. So really I have, the top is infinitesimal, right? I'm adding two infinitesimal, that's infinitesimal. The top is infinitesimal, but the bottom is finite, not infinitesimal, and so the whole expression is going to be, man, that's horrible. The whole expression is going to be an infinitesimal. Okay. How about 1 over epsilon times the square root of epsilon? So if I look at 1 over epsilon, so first off, you should recognize that's an infinite number. And if I multiply it by square root epsilon, which is an infinitesimal. So I've got a infinite number here and an infinitesimal here. Now that is exactly an indeterminate form. We come back up here, that's this form here, where we have an infinite number times an infinitesimal. So we are an indeterminate form, which means we have to do a little bit of algebra. We do have a relation between these guys, and so I'm going to rewrite this as epsilon to the negative 1 times epsilon to the 1/2. And if I have the same base, then it's just going to add exponents. So this is epsilon to the negative 1/2, or, if you will, 1 over the square root of epsilon. Now, the bottom is an infinitesimal, and so the reciprocal here must be an infinite number, and so this is an infinite, a positive infinite number. So 1 over epsilon times the square root of epsilon is an infinite number. Let's look at another example. So how about 2h plus 1? So this is a nice infinite number divided by, I don't know, let's say 3h plus 2. So question here, notice that 2h plus 1 is an infinite number, and 3h plus 2 is an infinite number. So this is an indeterminate form. It's exactly infinity divided by infinity. So our question here is, can we simplify this? Now this will be a strategy we use quite often. If I've got really large on top and really large on bottom, I will factor out the largest infinite numbers, largest power, if you will, of infinite numbers. Now, in this case, h is being raised to the first power. So I can factor that out. Probably not the kind of factoring you've ever really experienced in your algebra classes, but one that is very common in calculus. So I pull out I pull out the h, and then here I get a 1 over h. And what's nice about that is, remember, if h is infinite, then 1 over h is a infinitesimal. And over here I get an h factored out here, and this will be 3 plus 2 over h. And now these guys cancel, and I get 2 plus an infinitesimal, which is a nice finite number, over 3 plus 2 over h. And the top is finite, the bottom is finite, so this is finite, but not infinitesimal. It's not an infinitesimal. Right? So 2h plus 1 over 3h plus 2 is finite, but not infinitesimal. All right, we're going to pause this video right now, stop this video, and we'll do a handful of problems in the next and final video for this section.